is a perfect segue to our next presenters. We actually have two. Bob Bessemer is Vice President of Extrusion Technology. He joined the company in 2008, challenged with creating a new line of the most advanced and operator-friendly medical downstream equipment. Bob has a wealth of industry experience. He has worked for several downstream plastics extrusion equipment manufacturers during his 37-year career in product development, product engineering, and sales roles. And today he's going to be joined by Rich Vester. Rich is an extrusion product sales manager. He joined the company in 2013 and was responsible for their initial downstream extrusion design direction, sales of the line, and continued advancements. Since 1990, Rich has served in a variety of sales management, and product management roles in the industry. His background has been focused on single screw extruders, downstream extrusion equipment, and systems for pipe, profile, tubing, as well as sheet and film. Today, they're going to be speaking about move your process forward, make precision medical tubing with game-changing advancements in downstream extrusion. Messrs. Bessemer and Vester, the stage is yours.
Thank you. Well, my name's Bob Bessemer. I'm Vice President of Downstream Extrusion Technology.
I'm Rich Vester, the Downstream Extrusion Sales Manager.
And today we're going to be discussing the evolution of downstream equipment and how things have changed from normal extrusion to perfect the downstream equipment for the precision extrusion of medical tubing.
Thank you for listening to us today. There will be a question and answer period at the end.
We're going to start off today talking about how tanks have been modified. And a good place to start is start talking about the tank that we've developed here. This is a precision vacuum tank that's very similar to what's used in the medical industry or industrial. So the same tank could be used for straws, could be used for regular tubing or medical tubing. And we have advanced some things that we're going to bring to your attention here on this particular tank. And the biggest thing we're talking about at the start is how the splash tray, which would be a normal splash tray to help with condensation, has a dual function as a open reservoir system. And underneath it is our vacuum reservoir. And further underneath that is our water pump. So reservoir open, vacuum reservoir below it, and water pump below all helps the water move quickly and keep it from stagnating. It also helps in the cleaning ability, and you'll notice dramatically is the fewer number of hoses in a vacuum tank compared to most normal vacuum tanks. Other things that have changed on this tank is you'll notice we have used what's called a triclover fitting here, but in this particular tank, being that it's not a full medical tank, there are still threaded fittings here, and threads are known to be a difficult area for cleaning. Inside the tank, there are still threads that are being used, even the thread for the drain. There are threads that are exposed, very difficult for cleaning and flushing, and known areas for bacteria to grow. And rounded corners, these are typical rounded corners, not as rounded as we like to see. And at the bulkhead, you'll notice there are still welds. Welds are very difficult to clean, and again, a terrible place for bacteria to grow and reside. Other things that have changed, even though this is a more coarse tank, you still have up and down adjustment, you have linear adjustment, and you have side-to-side adjustment that are very fine. When we get into the more medical tanks, those adjustments have been made very, very fine, typically so you can get within thousandths, because you could make a tube that is only 5 or 10 thousandths in diameter. And you'll notice with this tank, being a non-medical as its main use, it's a steel welded frame that is painted, whether it be black or silver or white. Those things are difficult to clean. You'll see all the edges where it'd be difficult to wipe down. And next we're going to show you a tank that's been specifically designed for medical tubing extrusion. And this particular tank is an 8-foot open water tank, also made in a 3 and a 5-foot. But you'll notice right away in this tank that the frame is all stainless steel. Corners have been rounded, very few exposed bolts to wipe around. And on the front, the same thing, easy wipe down. Interesting, I've had people say that, Bob, you're making a pharmaceutical tank. Well, So much of the medical tubing today actually has pharmaceutical ingredients in it. So you need to have a tank that's for medical tubing that is designed for ease of cleaning. And with that, Rich, why don't you walk them through some of the features on this tank?
Okay. When we looked at this tank back here, it had small radiuses in the tank, welded ends, and what we've done now with the new medical tanks is we have a larger radius to fight bacterial growth. What a lot of people do is only go part way. They'll do the radiuses on the two linear sides, but it's very difficult to do on the ends. This tank here, as you can see, has it on the ends also. What this does for you is actually allows you a lot better cleaning. To go along with that cleaning, we also use triclover fittings. This gives you a sanitary fitting. It comes out of the beer and wine industry. It's FDA approved. No threads inside the tank. We also have movable rollers, which we'll talk about that a little more in depth over at the vacuum tank, but we include that. They're very important to have here because you don't want the product floating up out of the tank and causing stresses. We also have quick change tooling, which is very important for our customers. This is what it looks like, and it's just a simple eighth of a turn to put it in and fasten it.
And Rich, one more note real quickly is you'll notice on all the smaller tanks, we are having them not only passivated, but electropolished, which further inhibits the growth of bacteria. It's a known solution for this. So it gives a very shiny finish, which makes it difficult for the bacteria to grow on, which should lend to a lot more time between needed flushes or necessary flushes if you're finding your bacteria count in your water is too high.
And the one final thing for all of the tanks, when you have a tank that has a capacity that's not 100% what you need to have in the process, you're dumping water at the end of the day. We don't want that. So all of these tanks here have 100% capacity.
The other additional thing I wanted to mention, as with the first tank we showed you, we have taken it across all the line of medical tanks where the full-length splash tray is also your open reservoir. And then you'll notice that the water pump is down below. So after you've done a flushing, you can actually use the water pump to pump all the water from the contents of your whole unit for proper cleaning. All the water pumps in the medical tanks are put on AC inverters. They're variable speed. We're going to show you that shortly. And that's so you can actually minimize the RPMs and thus the vibration, unwanted vibration in a lot of pre-extrusion and medical tubing. And the water pumps are even mounted on vibration dampening units to further minimize any vibration. We don't want to see chatter or vibration in the water when we're making precise medical tubing. And we've just finished talking about the medical cooling tank series, which comes in a 3, 5, and 8 foot. And now we're going to talk about a medical vacuum tank. And a lot of the same features that have been on the medical cooling tank are moved over for the medical vacuum tanks, which also come in 3, 5, and 8 foot series. And Rich, why don't you walk them through this particular one, which is a 3 foot version.
Bob, on this tank, we still have the rounded corners like in the other tank, even on the short section like this, which are very critical. We have the triclover fittings, the full tray, full capacity water. Under that, we have a vacuum reservoir, which is all contained by itself. And under that, under this chamber here, we actually have the water pump. That's critical as on the other tanks because you need to have that water pump at the lowest point so you don't get cavitation. Now, if you notice on here, we don't have a linear movement. We've got side to side and up and down, but there's no linear adjustment. We have actually changed that now to a servo linear actuator on the back of the machine. Bob, would you mind showing them that?
And with that, everybody knows in medical, the hot gap, the actual distance between the face of the hot die and where the tube enters the water is a critical validation point. Because of that, that distance should be measured as it can change the properties in your medical tube, which are highly critical. So as you'll see, I can simply push on our touchscreen and push go to hot gap, and it will go exactly right to the thousandths of that hot gap. A very critical feature that we feel had to be repeatable. And of course, that's part of your recipe in this program, along with great things like having an AC inverter on your water pump, just like the cooling tank, having your vacuum reservoir on a slide so it's easy to clean. Again, all the surfaces are electropolished. And Rich, why don't you quickly show them what we've done again with your rollers. It's very important in vacuum.
In the vacuum tank, it's more important to have the adjustable rollers from outside, because when you're under vacuum, this lid is closed. So you wouldn't have, in a typical situation, you have to break that seal, lose your vacuum, and we don't want to do that. So with this, you have actually an outside application where you can get to those rollers real easy.
Also wanted to show you, we have a remote. It comes with all these tanks. Because we have a servo actuator, we want the operator to easily be able to take the remote, which is wireless, and they can do all the same features as they could with the touchscreen. So they can be up making adjustments on their movement of the tank, because you have to teach it the position of the face of the die to the tank when you initially start. So you can adjust that, you can move things, you can adjust your vacuum up and down. We can even interface and tie in the laser gauge so that it actually shows up your diameter on here. And we can show the position. We can change from daytime to nighttime on the water pump, so we can have the pump slowing down to keep the water circulation. Something else you're going to notice here, and filtration is a key item on medical applications. You need to go to minimally a 5 micron. In this case, we're actually going to 0.5 micron filtration, because the better the filtration, the longer the span is between time necessary flushes. Also is a UV light. UV lights basically is like a black light. It renders the germs sanitary, so they can no longer reproduce. They just die, become pyrogens, and the filter then filters those dead germ bodies out, the pyrogens. And now we're going to go into a little bit further detail about what we call the transducer holder. And this unit has been specifically designed with small medical tubing extrusion in mind. One of the most difficult things that processors have today is making sure that this tiny tube, and this tube could be 10,000ths of an inch, is the tube in the center of your tool. And for years, people have tried, can we use a camera there? And there are crossheads, and if we're right up against here, it's very difficult to see. So with these transducers mounted in its own water level controlled unit, we're water level controlling it and applying vacuum. And the reason we're doing that is so if we're right up 1/8 of an inch away from the face, we can make sure that water isn't coming out and hitting the die face and freezing things off. So we can literally have this tool 1/8 of an inch away from that hot die face, and we can actually display then with a crosshair on the screen of the ODID wall unit, we can display the position of that tube in relationship to those 4 transducers. So this is a tremendous enhancement for the processing of medical tubing. So in addition to actually being used as an ODID wall unit, giving you a hot unit reading for the OD and the ID in the wall up front, which minimizes the loop distance, as Rich was talking about, it is also helping us make sure that we are centered into the tool. And the next tank we're going to show you is what's called a Multipass tank that's been specifically designed for medical tubing. And what does a Multipass do? Well, for medical, it's saving a lot of space in a clean room. So the tube actually comes in, goes down through an open or a vacuum chamber, goes around a servo-driven wheel, comes back around a second servo-driven wheel, and then passes out through an air wipe section to what would become your third puller. And why would you have 3 pullers in line? For soft durometer flexible materials, being able to have your primary puller and secondary puller, we want to slightly slow down this puller to let the material relax in process. And the same thing with your external puller, let that be slightly slower than puller number 2 to further let the material relax. Along with that, we've gone one step further, is we have zone 1, zone 2, zone 3, which all can be independent temperature zones. And what we can do with that is we can effectively modify the material properties, say minimize the tack in a soft urethane. We can also, by using the 3 speeds, dramatically reduce the shrink back and be able to know what diameter tube you're making within 5 to 10 minutes of your process. Obviously, you'll notice a lot of other things, the same rounded corners, the same externally adjustable rollers, tri-clover fittings. So again, all these features very important, as well as, Rich, why don't you quickly show them The rollers can actually be lifted up to clean. So everything is designed to enhance medical processing. And now we're going to start talking about some of the modifications to belt pullers and things that have been changed to make them better adapt for being used for making small medical tubing. Of course, this is a larger puller, and this one is a poly V type of a belt, and this one does have hand cranks to open and shut the gap. And this particular one is a single servo, so, and for medical, almost everything should be servo motors now. Should not be vectors or DC drives anymore, everything's servo. But this one is a single servo, so there is a double-sided belt wrap, which people are starting to move away from. And with that, we'll go to a one size puller larger. And this particular one is a dual servo. Again, way too big for making a very small, precise medical tube. And we do have what's called the poly V belt, the same as the other one. We've taken the bottom belt off so you can see the type of a belt. And poly V tends to be a thicker belt, a lot of different coverings, but not necessarily the best. It's not very flexible when you're making a very small medical tubing, and we'll talk about that further. Rich, why don't you just touch base on the controls?
The standard machines now have come light years from where they used to be. Everyone now is moving to touchscreen controls, PLCs. This one here has recipes in it, so you can tie this into, again, all of your gauging systems and that sort of thing.
And of course, the gauging is extremely important. Any medical puller needs to be able to be interfaced into a full OD-ID and or wall system. And with that, let's move on to a small medical puller. This is an older unit, and we'll talk about some of the things that we've changed. So this unit too was a poly V belt. And this particular unit is a 3-inch wide by 12-inch traction, single crank wheel, so it's opening and shutting on a common center, still rather coarse. The biggest issue here that we want to bring note is as the material exits the puller, it's going to drape onto the table, which can lead to having what's called a wraparound, which medical people are very familiar with. So we're going to be showing some features on the next puller that's been specifically made and designed for medical tubing, which eliminates this issue. And now we're going to talk about specific medical design puller. And everything we've done here was specific, especially making what I call microbore tubing, small tubing, say a 1/16 of an inch and below, and they can be down to 5 or 10 thousandths with a 1 or 2 thousandths wall. So you'll notice the belt traction length is much shorter. You'll also notice that the either rolls are actually down below the two end rollers, so you have a controlled nip point. And on these little units, we are using what's called a flat belt. And they're much more flexible. And this particular belt even has a soft sponge with a silicone, which is FDA rated on the outside. So it's flexible, so we don't want to distort the material. In these small units, which this particular one is a 1x6, 1-inch wide by 6-inch traction. We also make a 1x12 and a 2x12. Both cases, the top and the bottom shivs are directly driven by a servo motor and an inline precision planetary reducer. This way, the shiv is direct driven and very, very precise. Using a flat belt gets rid of what I call a set in the belt, so you don't get a bumping. It's critical. If I'm running a very small product, that gap wants to be precise. Now, one thing that's occurred going from single servos to dual servos has been mismatch between the upper and lower speeds. And because of that, we've done some very specific work. And Rich, why don't we walk through what's been done to do an automatic software controlled synchronization of the upper and lower belt.
The issue that Bob was talking about is the actual length of the belt is never the same. There's always going to be a slight difference in them. So what that means is as the belts are traveling around on here, they're moving at a slightly different speed. Typically that doesn't create a problem unless you're doing low speed, rigid products, and then you'll get a stutter on the product and create a surface finish issue. What we've done is we've actually developed a process in here where we can, through our controls, we can actually tune the belts simply by doing that. And what's going to happen is the belts now are going to be moved apart and together. The torque is going to be tested both apart and together multiple times. It's going to look at that and figure out which belt is a higher torque than the other and reduce it to match the other. So even though those belts are slightly different in length, they end up with the same exact speed.
because it's operators can adjust one belt, tension one belt tighter than the other. There could be a slightly different gear in the planetary reducer. One's tighter than the other, anything, bearings. And having a servo boom has made this possible. So when I say servo boom, we're using a servo motor, planetary, and we're opening and shutting the upper and the lower boom independently. So we can get to a very precise gap, and we can actually go and tie into the laser gauge and say, I want the gap to be 5 thousandths less than the actual product. I call that a crush differential. So instead of operators cranking and saying, yep, I think I'm at the right tension, I'm squeezing in the right amount, we can have something that could be validated. So I want, for a 30 thousandths OD tube, I want a 25 thousandths gap, and that would be consistent from one operator to the next. So key for medical pullers is making everything consistent. So go to the most accurate servo motor to drive, go to the right belts, go to the right traction length, make sure the unit is able to be a walk-through type design, make sure the puller belt where the tube exits is in front of the table so material is going to come out and not go onto a table or hang onto a table. It wants to be able to drop down, so we minimize this wraparound issue. Obviously, the controls get far more extensive for medical. Again, the word validation, everything must be able to be tied into a host microprocessor if somebody has a host running the whole line. We need the laser gauge to be tied in. It can tie into our remote from our tanks. This particular screen is when we're doing taper tubing, so this is technically a full computer screen. So we want to be very visual. We want to see exactly what the gap is, and everything on the screen goes into the recipe management system. All of this is critical in making medical tubing. And this final segment, we're going to talk about modifications specific to cut small, especially small, flexible medical precision tubing. And a lot of changes have occurred. You're dealing with a small tube that could be so flexible, it's just a limp piece of almost like spaghetti coming out of the puller. And how can I push it and feed it into the cutter? So it's very important that the cutter be able to be on a dual slide rail and be able to be moved in and out. If I'm coiling, I can move the cutter out of the way. If I'm cutting, I want to string up. I can have the material going through, coming out. I can then cut it in, bring it through my bushings, and then I can slide it in. So things that are critical for medical, other than the slide, and being able to get it in very close to what I call the nip point. We've got a set of what we call bolt-together air feed bushings here. These bushings, I can adjust the amount of air going in and actually create a little bit of a vacuum to help draw the tube into the bushing. And also that helps, once the blade goes through, it helps to eject the part. It pushes the tube out. We also have what's called a lubrication system. So we can actually mist alcohol or distilled water right on the tube to help decrease the drag in the cutter bushing. So again, we want to be able to get it right up in there and be able to wet it, mist it. Very, very important. Other things for cleaning, just like in the tanks, we want to be able to clean this area out. We want to make this area very visible so you can see the blade. You can see if particulate's building up on the blade. People hate the word particulate, but particulate is a bad thing for medical tubing, whether it's a hair, a piece of dust, or a piece of flash. There's 3 different types of particulate. This tray can be slid out in the back and totally washed out very easily. We're using polycarbonate. You want to be able to see your blade gap. You want to see the bushings. You want to see everything. And so the other key thing is the speed of this blade arm. The length of the blade arm is specific, and the speed at which it passes through. You're wanting to get that blade through the part very quickly. And what I like to do is not chop, but slice. So the cutter head should be able to allow a blade to be put on a high slicing angle so we can draw the blade through. These type of cutters cutting small material can be using a blade as thin as 2 to 4 thousandths thick. So wetting the part, using air to enhance, using a very high-speed blade. This blade arm will actually spin through at up to 2200 RPM, which is twice as fast as most other units. Very critical. If I'm slicing, my blade is engaged in that tube longer, so I need my surface speed to be very high to get it through quickly. The other thing we're going to talk about is obviously these are servo driven, so that blade arm is attached right to the servo motor, very quiet, very precise. When you're making small medical tubing, a discharge conveyor is something that's very, very critical. So the tube comes out of the cut bushing, it goes onto the belt, which would be traveling a little bit faster than the actual puller speed. In these cases, the conveyor is actually, through the control, is made to follow the belt puller by percentage. So again, especially when you're doing recipes, you're not guessing how fast should the conveyor be. You can record that I was 3% faster than the actual puller speed. We do put a little roller here, just a little pressure roller to help when the part comes down. It's going to go under the roller, which you can adjust up and down. It comes down through, and it gets ejected into a side tray. You can see that a lot of little enhancements have been made for cutting medical tubing. We could spend hours talking about them. We really appreciate our time being able to present this to you, and thank you very much. Thank you for attending today. As you can see, there's a lot of evolution that has occurred, a lot of changes to the machinery, and we'll be glad to answer further questions later during the panel session. Thank you very much.
Thank you, gentlemen. That was an outstanding presentation, and I've known Bob long enough to know that when he says he can talk for hours about cutting medical tubing, he means he can talk for hours about cutting medical tubing. Now that was obviously shot in your lab. Could you give the audience some sense as to the equipment that you have in there that would be applicable to the medical market, downstream and otherwise?
All right. In the lab, starting off, we have a 1-inch medical extruder. We have a dryer in there, and we've been very thankful that we've worked with a lot of other people helping us in there. We've got full gauging equipment in there, full ODID wall. Mm-hmm. We've got chiller system. As far as the tanks, from the very smallest water and vacuum tanks we have in the lab, right up to 8 feet. And then we showed you a multipass tank. We showed the 8-foot that we did have at the last year's, the MDM show. Mm-hmm. That's the smallest size of the multipass tanks that we have. The little puller cutter is part of the new series. And probably the biggest thing we're trying to do is really change the level of precision and repeatability. And that's why we're using the servo boom so much. It's been something I've been talking about for years and years, is trying to make this process more consistent and repeatable. So that belt gap is so important. So full series of products in there in the lab, and it's available at this point because of COVID. We're having to do virtual tours or virtual demos, but we are proceeding with that.
The rollers that you showed, what are the materials of construction that you use?
The rollers in the tank, typically they're made of Delrin, but if somebody's making a very tacky product, they might be a Teflon material because we want to decrease the drag. And there's always been an argument, should the rollers roll or not roll, because a lot of people doing small free extrusion don't even want to see a ripple in the water. So we could have a discussion on that.
Could you give the audience some sense as to really what is going on in the medical tubing market now? Because I've heard kind of two things. I've heard on the one hand, processors are very anxious to get their hands on extruders to the extent that they are deploying lab lines or even buying lines that ordinarily would be used for R&D because the delivery time is better, and they're putting them into production because of the demand for medical tubing. On the other hand, I have also heard that because discretionary surgery is not going on to the extent that it was before COVID, that's kind of had a negative impact on this particular market segment. Like, what's going on out there?
And your last statement is very true. Rich and I have both heard that from multiple people. People are having discretionary surgeries. It was shut off for 3 to 4 months. It's back on, but people, I think, are still afraid to go in to the hospitals. And I think that's going to continue probably for another 6 to 8 months until we have a really good solution that everybody's, we've got this thing under control. So until then, I don't think people's budgets have been canceled. They've been delayed because a lot of that disposable tubing isn't being used. To me, this is a time when people should be taking advantage of better technologies. Because things that we're trying to do, especially, is trying to enhance this process, help our processors be more precise, go faster, and use less labor.
Right.
It's so those things are more important. I do think over the next few years, because of this, it's a terrible situation, but I think medical tubing is going to be a huge area in the plastics industry. I think it's going to grow, and I think technology, everything that can be improved is going to be taken advantage. It's just a tough time for all right now.
Right. And, rightly or wrongly, fairly or unfairly, I think the North American plastics processing market has a reputation as being one that doesn't adapt too quickly to change. And what you have here is you have a whole suite of new solutions for the medical market. Is the medical market any different in that regard, or do they like to wait and see?
It's been interesting, and it's been tough over my long career. I've tried to be on the forefront of new technology as you've been involved my whole way through. You and I followed each other. And over those years, I've come out with, through the companies I've worked for, come out with a lot of new developments, and it's very typical. And I keep telling everybody, you have to be patient. New technologies, I don't know what it is in extrusion, but it takes a long time, anywhere from 1 to 5 years for new technology to catch on. And you have to be patient and not walk away from it. People will finally, all of a sudden, a year later, 5 years later, everybody will be doing it. But and you just wonder, why aren't people using this new technology? It's here, it's now. But change is difficult for a lot of people and a lot of companies.
Bob and Rich, do you see much in the way of medical tubing coming offshore, coming from China, coming from other Asian countries?
Finished tubing, not so much. We are seeing assemblies still being done that way, but everybody seems to be reshoring everything.
Okay. All right. John, any
to go along with that, it's a lot of the companies that were producing in China were producing for China. It wasn't being shipped back over here or in different countries. I think there is some what I call commodity tubing that was made outside being brought in, but more and more, I think you're going to see a lot more manufacturing for those products here, so we don't have to depend on them shipping from external places.
Right. So, Bob, we talked a little bit about the North American market and their acceptance of new technology and how it's a wait and feel and look and touch before they really wrap their arms around it. Do you have any sense as to what the European market is with respect to medical tubing? I mean, would they view some of the things you've developed as groundbreaking as well, or are they already a little bit ahead of the curve?
Well, it's funny because in medical, people always thought that, or in profile and sheet and everything, that the Europeans were ahead. In medical, I think in the U.S., we are the leading technology. And interesting, as far as people being interested in the new technology, we're seeing probably a 50-50 mix right now between Europe and the U.S.
Right. Bob and Rich, do you look at the medical tubing market as perhaps a market in which someone who is making high precision tubing for other applications should think about exploring, or are the barriers to entry such that, if you want to be in medical tubing, it's best to be in medical tubing and not try to take technology from another market?
Rich, you want to?
Sure. Actually, we see a lot of the people in the other industries getting more involved in medical tubing. Obviously, everything's been slow, so they're taking that time and actually researching this very well. We have customers that we talk to every day that ask us for quotations for equipment.
Okay.